All right, welcome everyone. So today we are talking about consistency, which is our third way of assessing estimators and choosing which ones are better. So we talked last week about things that make estimators good. And we said that an estimator was unbiased if the average value of the estimator, theta hat, over many samples was equal to the thing you're trying to estimate. So call it theta. Hey, Vivian. All right, but that's so the average over many samples. And in practice, you usually only take one sample of size n.
I think it really helps people think about
So intuitively, we want our estimator theta hat to be better when we take a larger sample. And by better here, we mean closer to theta, closer to the thing we're trying to estimate.
Yeah.
So theta hat is defined as a consistent estimator for theta if for all values of epsilon greater than 0, so for all distances that we want to be within that closeness of theta, the limit of the probability that theta hat sub n minus theta, absolute value, is less than or equal to epsilon, that limit is equal to 1. So this looks pretty technical, but really all it's saying is however close to theta you want to be, you can get there with probability approaching 1 by taking a sample size that's large enough.
Skin impression size of he had it in this like extremely protective case in like the back of the back of the truck.
When theta hat is an unbiased estimator for theta, then we have another way we can use to check if it's consistent. And that is if the variance of theta hat approaches 0 as the sample size approaches infinity. All right, so for example, in our lab yesterday, we were estimating the mean beta for an exponential distribution. And we had two different estimators. Beta 1 hat was y bar, and beta 2 hat was n times the minimum of the y sub i's. And you saw that when we simulated them with beta equal to 2, they both had means that were close to beta. So that tells us that they're probably both unbiased. But the probability that beta 1 hat was within 0.4 of beta of 2, that increased when we increased the sample size. And the probability that beta 2 was within 0.4 of beta didn't increase. It stayed about the same. So that's suggesting that beta 1 hat is a consistent estimator for beta, and beta 2 hat is not. So we can control how precise beta 1 is by increasing the sample size, but we don't have that same level of control over beta hat 2. Questions so far? All right, so let's try to prove that our empirical results from lab yesterday are actually true. So let's prove that if the y sub i's are an independent and identically distributed sample from an exponential distribution with mean beta, then y bar is a consistent estimator for beta. So let's start by checking if this estimator is unbiased. Because if it is, then we can check if it's consistent by checking its variance. So the expected value of y bar is the expected value of y sub I, which is beta, the mean of the exponential distribution. So the expected value of our estimator equals the thing we're trying to estimate. That means it's unbiased. So that means that we can check whether it's consistent by checking its variance. So the variance of y bar is equal to the variance of y sub I over the sample size n. And we went through this proof in lab yesterday during our review session. So why don't you take a moment to try to sketch that proof out for yourself. And go ahead and talk about this with someone sitting near you. So here's what I said. I started by writing the variance of y bar as the variance of what y bar is equal to. So the variance of 1 over n times the sum of the y sub i's. I pulled out the 1 over n outside of the variance, so that becomes 1 over n squared times the variance of the sum of the y sub i's. Then the variance of the sum of the y sub i's, in this case, equals the sum of the variance of the y sub i's. And that works because the y sub i's are independent. So that works because when you do the table method, you have y sub 1, y sub 2, dot, 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 y sub n, y sub 1, y sub 2, dot, 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 y sub n. All the entries of this covariance matrix on the diagonal are going to be the variance of the y sub i's. And all of the non-diagonal entries, so the covariances, are going to be 0 because the y sub i's are independent, so their covariances are 0. So the sum of the entries in this table is the sum of the variances of the y sub i's. That is the variance of sum of the y sub i's. Questions about that part? All right. Vivian asks, is this still under MLE? So here we were just given these two estimators. So this is consistency. And in this problem, we were just given these two estimators. And we're trying to figure out whether either of them is consistent. We're trying to prove that beta 1 hat is consistent. In fact, if I recall correctly, beta 1 is the MLE, but we haven't shown that yet today. Yes, so this is another subchapter. Sorry. You missed the first slide where we were saying this was the topic of consistency. All right. Share my screen again. Okay, so we have that the variance of y bar is 1 over n squared times the sum of the variances of the y sub i's. But all of the y sub i's have the same variance because they all have the same distribution. So this is just the sum of n copies of the same variance. So that's just n times the variance of one of the y sub i's. And then we can cancel an n with one of the n's from the n squared here. So we get that the variance of y bar is the variance of y sub I divided by the sample size n. So this is not exclusive to the exponential distribution. The only things we used in this proof in the red box are that the y sub i's have the same variance and are independent. All right, okay. So finding the variance is going to let us use this approach for checking whether our estimator is consistent.
All right.
Because we showed that it was unbiased, so this approach will apply. Davis.
Does this approach work, but if it doesn't approach 0, it's not consistent?
That's a great question. Our book only specifies it in this direction. So if the limit is 0, then it's consistent. I did not spend the time to work out if the proof works in the other direction. In practice, I think this idea is a good way to understand why an unbiased estimator is not consistent if the limit of the variance is not 0, because you sort of have this same amount of variability around the mean that you're trying to, the true value that you're trying to estimate, and you can't converge and get enough closer for it to be consistent. But when we're looking at beta hat 2 and trying to show that it's not a consistent estimator, we'll do that by picking an epsilon and showing that the probability of being within that epsilon doesn't approach 1. Does that answer your question? All right. All right, so our variance of y bar is the variance of y sub I over n. Oops, I need to go through that again. So then the y sub i's had an exponential distribution. So we can fill in the variance of y sub I with the variance of an exponential random variable, which is the square of its mean. So then the limit of the variance of y bar as n approaches infinity is the limit of beta squared over n as n approaches infinity. So beta is a constant. So as n is approaching infinity, that limit is going to be 0. So that proves that y bar is a consistent estimator for beta. So however close we want to get to estimating beta, we can get there with sufficiently high probability approaching 1, by increasing our sample size. All right. So now let's take our other estimator. So let's take y sub I as an independent, identically distributed set of random observations from an exponential distribution, same as before. Let's prove that n times the minimum of the y sub i's is an unbiased estimator of beta. So to think back to our order statistics, the general density function for the minimum, so y sub 1 in parentheses, is n times 1 minus the cumulative distribution function big F raised to the n minus 1 times the density function little f. So if we take the density function and CDF of an exponential distribution and plug them in here, we get this thing. We get n times 1 minus e to the negative y over beta, all to the n minus 1, times 1 over beta e to the negative y over beta. So we can simplify this. The 1 minus 1 is going to be 0. So we end up with n over beta times e to the negative y times n over beta as our density function for y between 0 and infinity. Take a moment to think to yourself what density function this looks like. And then talk it over with the people sitting near you. Nice. Yes, this is an exponential distribution with mean beta over n. So this is similar to the problem you did on homework 0 about the headphones. All right, So now we're trying to prove that n times the minimum is an unbiased estimator for beta. So we want to find its expected value. So that's going to be n times the expected value of the minimum. And the expected value of the minimum we just found was beta over n. So we have n times beta over n, which is beta. So that's proving that our estimator, n times the minimum, is an unbiased estimator for beta. Questions so far? All right. So now let's find the variance of this estimator. See if it approaches 0 as n approaches 1, or n approaches infinity. There. All right. So start by pulling the n out. So we get n squared times the variance of the minimum. And what did we say the variance of an exponential random variable was? Kyle?
Mean squared.
Yeah, it's the square of the mean. So we have n squared times the square of beta over n. So the variance of n times the minimum is beta squared. So this does not decrease as the sample size n increases, which means that increasing the sample size doesn't improve the precision of this estimator. Kyle.
Consistency.
Right, we're getting there. Everything's interconnected. So what this shows, let's go back. This shows that we cannot use this theorem to show that beta hat 2 is consistent. That strongly suggests that it's probably not consistent. But our book does not actually have a proof in the opposite direction to prove that if it's consistent, then the variance will approach 0. In order to actually prove that it's not a consistent estimator, we want to pick some epsilon and find the probability of being within that epsilon of the true value of the parameter beta. And we want to show that that probability doesn't approach 1 as n approaches infinity. So here we're using epsilon equal to 0.4, which is the same value that you used in lab yesterday. All right. So we can expand this to say that this is the same as the probability that our estimator, n times the minimum, is between beta minus 0.4 and beta plus 0.4. And then we can divide everything in this inequality by n. So we get the probability that the minimum is between beta minus 0.4 over n and beta plus 0.4 over n. And now we can use the fact that the minimum has an exponential distribution and say that this is the probability that the minimum is less than or equal to beta plus 0.4 over n minus the probability that the minimum is less than beta minus 0.4 over n. So the big F here represents a cumulative distribution function for an exponential distribution. We're not talking about the F distribution here. Alternatively, we could have taken the density function for an exponential and integrated it from the lower endpoint to the upper endpoint. That would also work. All right. So when we do that, we get the CDF for an exponential distribution. So 1 minus e to the negative, oh, sorry, that should be 0.4, not 0.5. So 1 minus e to the negative value we want to find the probability of being less than, divided by the mean. So divided by beta over n. And then minus the same thing, but with the other endpoint. So this simplifies to e to the negative beta minus 0.4 over beta minus e to the negative beta plus 0.4 over beta. So for example, when beta equals 2, that equals 0.1481, which hopefully should be close to what you got in the lab yesterday for the proportion of samples that were within 0.4 of a value of 2, both when you had a sample of size 5 and when you had a sample of size 100. So crucially, we see that n doesn't appear anywhere in this probability. So this probability doesn't increase, it doesn't approach 1 as n approaches infinity. So no matter how big the sample size is, we can't improve the chance of beta 2 hat being close to beta. So this proves that beta 2 hat is not a consistent estimator. Questions about this? Sam?
So we can only use like the limit of the variance if the variance depends on n.
So the limit of the variance is only informative if theta hat is unbiased. And this is only a way to prove that theta hat is consistent if the limit of the variance is 0. If the limit of the variance is something else, then technically this theorem doesn't apply. Other questions about this? Joey?
Is choosing the value 0.4, that's just kind of like the common move to do?
It's just sort of a nice convenient value that where you don't get a probability that's super close to 0 or 1. So I wanted to choose the same value here as we used in lab yesterday. As far as proving that something is not consistent, if you can find any epsilon where this limit doesn't equal 1, then you've proved that it's not consistent. So if you pick 1 and find that the limit is not 1, then you're good to go. I suppose it's theoretically possible that there could be an estimator where this works for epsilon equal to 0.4, but not for epsilon equal to 0.3. But that would be a pretty unusual estimator. Other questions about this? All right, we have about 10 minutes left. So let's take a bit more time to work on our maximum likelihood estimation. And I'd say let's come back to problem 3 on Monday, and let's tackle problem 4. So take a moment to try writing out the formula for the likelihood of theta for problem 4. right, so the likelihood is the joint density of the y sub i's. And assuming this is a random sample of independent observations, we can split that up into the product of the densities of each of the y sub i's. The density of each y sub I is 1 over theta minus 0, so 1 over theta. And we can write that as the repeated product as I goes from 1 to n. So that's just 1 over theta to the n. As long as the y sub i's all satisfy the support, the range of possible values for a uniform distribution. So as long as the y sub i's are less than or equal to theta and greater than or equal to 0. All right, what's the next step? Okay. Let's take the log. So the log likelihood. So the log of 1 over theta to the n, it can be log of theta to the negative n. And then we can bring the constant outside of the log. Negative n log of theta. What's our next step? Okay. Now let's take the derivative. So the derivative with respect to theta, because that's what we're trying to estimate. So we have negative n times the derivative of the log of theta, which is 1 over theta. So negative n over theta. What's the next step? Before we solve, we should set this equal to something. What should we set it equal to?
0.
Set it equal to 0. All right, so now as Sam said, we want to solve for theta to find the critical points. What's the problem here? Okay.
As soon as you multiply the theta over 0.
Right. So there is no value of theta for which negative n over theta equals 0. So there are no critical points to this log likelihood. So if we can't find the maximum by setting the derivative equal to 0, how do we find the maximum? Kyle?
We derive it again. So try to see how kick up or down.
So taking the second derivative would tell us about concavity, but it wouldn't give us any critical points that we already don't have. Niall?
You use the endpoints in your intro.
Yeah. So the fact that there are no critical points here mean that the log likelihood is either always increasing or it's always decreasing. So there's no maximum. And if it's always increasing or always decreasing, that means that the maximum has to be at an endpoint. So that's where we'll pick up on Monday, finding which of the endpoints is the maximum. I'll see you then. You're welcome, Vivian.